Welcome back, everyone. In this video, we'll be going over the rest of the substitution method section. And in this video, we'll focus on substitution method with definite integrals. All right, so when you use substitution method with definite integrals, it's mainly the same steps because you're going to have to go through and do the same substitution. The question is how you plug in the numbers here. So with a definite integral, we know we plug in the top number, subtract, plug in the bottom number, and we do that after we compute the antiderivative. Well, how are we going to actually do that? Well, the main issue is going to be here when you're starting off, all of our values are x here. So this is telling you to plug in x equals 1 and x equals 0. You don't have to write the x equals part, but because we're starting with x's and we want to integrate from 0 to 1, it's telling us at the end, after we do the antiderivative, plug in x equals 0 and x equals 1. All right, so I'm going to do it the way most people, when they see it the first time, prefer, and then I'm going to show you another way, and then from there, you'll just pick the way you prefer to do problems going forward. Okay, but why do we need the substitution method in this problem? First of all, well, the one thing I think of in this problem is that I don't have an integral formula for e to the anything besides x. So I should probably make u equals to this because I do not have a formula otherwise. So we want to go ahead and make u equals to that exponent. If we integrate e to the u, it's just fine. E to something else, not so good. So we got u equals negative x to the 11th. Well, what is du? We just have to do the power rule here. We get negative 11x to the 10th dx. And if you go through and solve for dx here, which once again I recommend, we divide by the negative 11, x to the 10th on each side, and we get du over negative 11 x to the 10th equals dx. All right, so let's go ahead and plug in. But as I write down the integral at every step, I'm going to write not just 0, but x equals 0 and x equals 1, because I want to emphasize what we're doing here. All right, inside x to the 10th, that was not part of u. Hopefully it goes away. The next part, we have e to the u power because we made the exponent u. And in place of dx, we have du over negative 11x to the 10th. Now, one thing I guess I didn't mention in the previous problems is that you cannot factor out things with u because that's our letter of integration, but u and x are related, so you can't factor out anything with x's either. So really, you do need these to cancel out, but they do. We have x to the 10th on the top and bottom. So we're good. And we can also take this negative 11. Keep in mind it's on the denominator. So when we bring it out, this comes out as negative 1 over 11. All right. So let's go ahead and write what we got. We got negative 1 over 11. And we have integral from x equals 0 to x equals 1. And we have e to the u du. Well, what is e to the u? The antiderivative of that's just itself. We got negative 1 over 11, e to the u. Because it's a definite integral, we do not want to add a plus c. We don't need to. We can just plug in our evaluation bar, x equals 0 to x equals 1. But this is a big reason why I like to write it like this, especially when you do substitution method. What's the easiest mistake to make here is to plug in 1 and plug in 0 without realizing that our integral at the beginning said plug in x equals 1 and x equals 0. But this is u. So what do you have to do first? Well, you have to do the same thing you do for the indefinite integrals. You have to plug back in what u is. Because we don't want to plug in u equals 1, we want to plug in x equals 1. We go ahead and take our formula, plug back in. We've got negative 1 over 11 e to the negative x to the 11th power, evaluated. And if you want to not write the x part because it's matching anymore, that's fine, but I'm just going to keep writing it. And now everything will make sense. We plug in x equals 1, we subtract, we plug in x equals 0, and everything should be good. All right, so we got negative 1 over 11 e to the negative 1 to the 11th power, plugging in x equals 1. And then we also have minus negative 1 over 11 e to the negative 0 to the 11 power. Now, we have just 1 to the 11th here, which is 1, and then a negative sign gives us negative 1. So the first part here, this is going to be negative 1 over 11 e to the negative 1. This is a minus minus, gives us a plus, and then anything to the 0 power is 1. So this is just 1, and we have plus 1 over 11, because this is just equal to 1. All right, so now that we got that established, that's pretty much a good answer. If you want, you can't really go further because e to the negative 1 is going to be a messy decimal, and we aren't told to use a decimal here, so we need this as our answer. The only thing you can really do is if you want to factor out the 1 over 11, you could. So this would be negative e to the negative 1 plus 1. And you can do that, or you can leave it like this. It doesn't really matter. But that's one way. What's the other method? So this is the method where you either convert everything back to your original variable. That's exactly what we did. So we converted everything back to x, then plug in the bounds. So we did method 1 here. I'm going to label this as method 1. And this was method 1. All right, so what is method 2? I'll use the same color. Method 2 is going to be, you can use your substitution formula to change the bounds on your integral. And then once you change these, so if we plugged in 0 for x and 0 for 1 and figure out the u values here, we could have just plugged in u values at the end. And this will be method 2. Let me actually highlight that with a different color to make it more clear. Green. All right, so then we can use a substitution formula to change the bounds on your integral and then use those bounds. And this will be method 2. I'm just color coding it here. So when we do method 2, everything is going to be the same at this step. So you start with your original integral. You have x equals 0 to x equals 1 of x to the 10th e to the negative x to the 11th dx. Now you don't go through and do anything different when you make the substitution. You still want to do the same exact thing. So I'm going to go ahead and just fast forward to here, because we would do the same exact thing, plug in the same stuff and simplify. So you have negative 1 over 11, x equals 0 to x equals 1 of e to the u du. But here's the big difference. Before you integrate, what you want to do for this method 2 is plug in and figure out what should u be. So we want to plug in x into formula for u, the one we have right here. And we do that for both of those. So I'm going to go ahead and actually just set this up here. This is the way I like to write it. I like to write it right below. You can write it on the side, whatever is best for your organization. When we plug in x equals 0 to our formula, we get u equals negative 0 to the 11th, which is 0. And then when we plug in x equals 1, we get u equals negative 1 to the 11th, because that's our formula for x, which is negative 1. Now when we integrate, I'm not going to actually integrate yet. I'm going to plug in those bounds. So I have negative 1 over 11 in front. In place of x equals 0, I now have u equals 0. In place of x equals 1, I have u equals negative 1. And we have e to the u du. So all I did was I substituted on the integral the bounds from our formula. But the nice thing is after you integrate this, we got negative 1 over 11. The integral of e to the u is e to the u. We're plugging in u values. Yeah, we have the bigger number on the bottom. 0 is bigger than negative 1, but as we saw before, it doesn't really matter if you have the bigger u value, if you have the bigger bound on the top or bottom. So we can just do this directly. We can plug in what u is because it already matches the letter. So we can plug in u is negative 1, subtract and plug in u is 0. So let's go ahead and do that. When we plug in u as -1 on top, we have -1 over 11 e to the -1 minus u to the u equals 0. We get -1 over 11 e to the 0. And the reason why I prefer doing this way is just because if you do it this way, then everything's kind of already simplified. You didn't have to simplify the exponent in 2 spots. You just did it once. Really, when you plugged in back here, and then simplifying is easier. But you have the same exact thing. So we have -1 over 11 e to the -1. Minus minus gives us a plus. Anything to 0 is 1, so it's plus 1 over 11. And that's exactly what we have here. And you can factor out the 1 over 11 if you want to kind of finalize simplifying it. But the point is you should use whichever method you like, method 1 or method 2. It's up to you. All right, but I just realized that I wrote method 1 up here, so let me rearrange and say this is method 2. All right, but once again, pick the one you prefer. Most students, when they're learning this, like method 1 more than method 2 because it feels like you're doing the same thing as when you do the indefinite integrals. You plug back in for u at the end. Method 2 is more like, well, we kind of have a shortcut for plugging in because we have a formula for u already, but pick the one you prefer. Whichever one speaks to you, do that one. All right, so number 2 here is just kind of a word problem, but it gives you everything and really tells you how to set it up. So it says a model for the basal metabolism rate and k calories per hour of a young man is given by r of t equals 65 minus 0.8 cosine of pi over 12, or sorry, pi t over 12, where t is the time in hours measured from 5 a.m. And it says, what is the total basal metabolism of this man? That should probably be just man. And it even tells you how to do that. The integral from 0 to 24 of your rate of change here over the first, or over a 24-hour time period. Now you can imagine why this thing is a trig function is because it's periodic. What happens on one day should happen pretty much the same on the next day. And we really only want to do the problem that it's telling us. We want to integrate from 0 to 24. And we have the function 65 minus 0.18 times cosine of pi t over 12. And then we want to make sure we do dt. All right, so what do we want to do here? Well, one thing you might notice is that we are linked by a minus here. We actually don't want to try to think about use substitution on the whole thing. But the nice thing is that you can break up the integral in each part if you prefer. And it might be a good idea to actually do this, especially if you have multiple parts when you have substitution method. So what we do is we can break it up into just the 65 dt minus the integral from 0 to 24 of our other function, 0.18 cosine of pi t over 12 dt. Right, now why do we want substitution method here? Well, it's because this is not just t. So we want to make u equals pi t over 12. All right, and once again, that's really the same method as before. We're looking at the same thing, same kind of thing. We have u equals whatever the inside of our trig function is because it's not just t. And then du, well, the derivative of this is just pi over 12 times dt. And like always, I like to solve for the thing. So I want to solve for dt. I want to multiply by the reciprocal 12 over pi. So I'll do it over here. And I'll do that to each side so that I have dt solved for. We have 12 over pi du equals dt. All right, now you can actually go ahead and integrate this one because this is just a number. So you get 65t. We want to evaluate from t equals 0 to t equals 24. Keep in mind these are t values. Minus, and if you want, you can bring out the 0.18, the integral from t equals 0 to t equals 24. And we have cosine of u. So this whole thing is u. We brought the 0.18 out. And then in place of dt, we have 12 over pi du. Now it's up to you. What do you want to do from here? Do you want to plug in what t is to figure out u values, or do you just want to plug in at the end what our formula for u is and then plug in the t values like we did in the previous problem? Just pick the way you prefer. Maybe go ahead and pause the video and do it the way you prefer and see if you get the correct answer compared to what I do. But I'm going to go ahead and first move this 12 over pi out just to make my life a little easier. Now in the front here, this is just t values. There's no substitution in this front one. So we have 65. And then we want to plug in t equals 24 minus t equals 0. Actually, let me go ahead and spill that out in 2 steps here, because this is going to be useful going forward. If we plug in 24, we have 65 times 24 minus 65, plug in 0. But what's often going to happen is when you have just numbers, you're only really changing where you plug in t, so everything else remains the same. So when we go to the next step, instead of just figuring this out, I'm going to purposefully factor out the 65 so you can kind of see a little shortcut. All right, but this is the first part. And then the second part, go ahead and highlight this part in green. We have minus, we have 0.18, factor out the 12 over pi, and then we integrate from either the t values or you can plug in the u values. As I know, most students prefer just plugging in back in what u is at the end and then using the t bounds. So I'm going to do that. Well, what do we have left inside to integrate? T equals 24. Well, we only have cosine of u du. All right, let's go ahead and keep simplifying now. So like I said in this first part, even though we could easily just type this in the calculator, I'm going to go ahead and write this with the 65 factored out. So we have 24 minus 0. And the reason I wanted to do that is to show you that really what we're doing here is we can think about the 65 being factored out, and then we just do 24 minus 0. That can be helpful to do. All right, and then we have minus 0.18. Go ahead and write that down. 0.18 times 12 over pi. And then because we're multiplying this by the integral, I'm going to go ahead and write it in a bracket. The antiderivative of cosine is just sine, so we get sine of u. We want to plug in t equals 0 to t equals 24. So at this point, we have to, since I didn't substitute what my bounds are, I need to go ahead and plug back in what u is. U is pi t over 12. All right, now we can go ahead and type this in the calculator. What is 65 times 24? 65, oops, that's multiplication, times 24 is 1,560. And then we have minus 0.18 times pi over 12, or sorry, 12 over pi. And in place of u, we need to put in the pi t over 12. And we're going from t equals 0 to t equals 24. All right, and one more step and we'll be done, because now we can finally plug in. We got our 1560 in front, minus. Now, just the way I did it last time with the 65, and I kind of showed you here, I'm just going to leave this stuff out front, the 0.18 times 12 over pi. And then I'm going to go ahead and put a big bracket around and plug in t equals 24 minus, and then t equals 0. All right, so this is sort of like the 65, and this is sort of like the t that we plugged in. I'm just going to apply this right away because it's much more helpful than actually writing this times this minus this times this again. So t equals 24. If you plug in 24 for t here, you get 24 pi over 12, which is 2 pi. So it's sine of 2 pi. Minus t equals 0, well, we get sine of 0. And hopefully you remember, but if not, you can type in your calculator. Sine of 2 pi and sine of 0 are both 0. So in fact, we're multiplying this thing by 0 and that goes away. So we're just left with 1560. So oddly enough, even though this stuff caused way more trouble, it ended up integrating and giving us exactly 0. So the front part was really the only part we needed. Now that can happen, but you don't know if that's going to happen until the end. So don't try to use a shortcut like that. And especially if you don't go over all 24 hours, that's not going to happen. But this is pretty much the way substitution method works for definite and indefinite intervals. It takes a lot of practice, so make sure you are doing the practice, and I will see you in the next video.